Okay, your mics are live. Hello, everybody. Welcome back to the Telescope Talk Pro Hangout, a weekly hangout that is designed to get us informed and caught up on all the really great professional activities in astronomy that's going on in ground-based observatories around the world. And today we are going to talk about dark energy, in particular, the Dark Energy Survey, which is a group of scientists from all over the world who have built a camera, a 500 megapixel camera that they're calling DECam, and they've put it on the 4-meter Blanco Telescope at the NOAO, the CTIO observatory in Chile, and they have been looking at the sky for over 700 nights, and we're going to talk about what they were doing and why. But mostly, it's in an attempt to characterize this elusive stuff we've come to know as dark energy. And so today we are going to be talking with a member of the group of the Dark Energy Survey, which just finished its survey, and we'll talk about the observations. We're going to talk about the equipment and the things that have been going on with this really, I think, a really great program. I actually worked for them for a couple of years, so I'm very excited to get a status update on this as well. So before I begin, let me introduce my co-host, Christian Reddy from Launchpad Astronomy. Hi, Christian, you out there?
Hey, Tony, how are you? And thank you very much, everybody, for joining us both on Deep Astronomy and on my channel, Launchpad Astronomy. I'm Christian Reddy, your friendly neighborhood astronomer. And I don't know about you, but my universe has been accelerating uncontrollably for the last 13 billion years. And that's why I'm very happy to welcome our guest, Dr. Ross Cawthon, who's from the Dark Energy Survey. And as Tony said, is going to be telling us a lot more about the Dark Energy Survey and about the quest for dark energy. So thanks for having me aboard, Tony, once again, and welcome, Ross.
Yes, welcome, Ross. But before, hang on, I gotta say a couple things. The Telescope Talk Hangouts are sponsored by OPT Telescopes in Oceanside, California. These are a world leader in telescopes and accessories for both amateurs and professional astronomers. So I want to thank them for their support, without which we would not be able to stream this hangout to you. So thank you, OPT. And also let you know that in addition to my channel on YouTube and Christian's channel on YouTube, we're also streaming to the Deep Astronomy Periscope account, as well as the Twitch account. All of these chats are being coagulated into my chat window, and I can see them all now. We also have a Discord server, which, if you would like to join, the link to that is in the description box of the video on YouTube. So please join us on Discord as well. Okay, now let me bring up my guest. Our guest today is, I was showing Christian that whole time. I need to turn on auto switch. Hang on just a second. Auto live. There we go. My guest today is Ross Cawthon. He is from the University of Wisconsin-Madison and a member of the Dark Energy Survey. Welcome, guys. Or welcome, Ross. It's good to see you.
Thank you. It's a pleasure to be here.
All right. Well, so the Dark Energy Survey. Why don't you tell us, first of all, give us a big summary of what the project is, and then we'll talk about what you hope to accomplish.
Sure. So like you said, this was a large sky survey that we observed for more than 700 nights. We just finished last Wednesday night, so that was a big milestone for all of us. And so we're observing a full eighth of the sky, so 5,000 square degrees of the southern sky. For most of the survey, the goal was to get very deep images, to get many galaxies and many other signatures to infer cosmology that we'll talk about. So we observed most of that sky for a total of 10 times in 5 different color filters. There are also a few areas that were called deep regions, where we observed for longer periods of time. Those are specifically for type 1a supernova. So those are kind of the two phases of the survey, these deep regions and then a larger sky survey. And it's one of the deepest, largest surveys in the field right now. I think by volume, it is the largest survey presently. And we've done a lot of different science with it.
Now, this is the first of what is going to be many surveys going from ground-based observatories. Did you send me, with all of your images, did you send me one of them that had a the coverage of the survey itself, or do I not have that? Were one of these,
I
like
think
the DES stellar stream one, would that show the coverage?
Yeah, that shows the coverage. You could show that.
All right. So what I've got up now, folks, is a image of the 5,000 square degrees that Ross was talking about. This is what they were looking at skywise. Now, you're limited with ground-based telescopes on where you can see. And this was designed, as I remember, to overlap a lot, or at least to overlap some of the stripes from the Sloan Digital Sky Survey, which is a much older survey, but up until this one was one of the most complete surveys. Is that correct?
Yeah, definitely. So the survey was designed with a few different other surveys in mind. So as you said, I'd say the main precursor to DES is the Sloan Digital Sky Survey, and that was in the north. So it was important that we had some overlap with that survey, and that's been useful for a number of different reasons. So having some coverage in the north was important. That strip at the top of that image is all overlap with Sloan. What was also important is overlap with the South Pole Telescope, which studies the cosmic microwave background, which is, as its name implies, is in the South Pole. So that covers mostly that wide region at the bottom, which is further south. And so we have complete overlap with that, and that's important for a lot of cosmological studies as well. So it was important to cover mainly those two surveys.
Okay, so you're covering 5,000 degrees of the sky. Let's show the camera itself. I'm going to show, I think, where it says, here it is, DECam close up. Let me show that. That's the camera, folks, and each one of those little squares. Well, you describe it for us, Ross. What are we looking at here?
Sure. This is the dark energy camera. You can see the chips there in blue. So overall, it's, as you said, 500 megapixels. At least at the time when this was installed in 2012, this was, I think, the most powerful CCD camera in the world. It was a really special type of camera. I won't be able to get into super fine detail, but these were a new kind of CCD that was better for studying infrared light as well. So we're studying high redshift galaxies to do cosmology, and a lot of that light gets redshifted into infrared. So it was a technological achievement, this dark energy camera. And just to give some more context, so our survey uses the Blanco Telescope, which we can show in a moment. That telescope has been around since the 70s, so it's still a great telescope. It works well. But the real technological advance that we used for the dark energy survey was this dark energy camera. So that really allowed this great science we're doing with DES.
So, Colton, I got a question for you about the camera, but I want to go back briefly to the actual survey region, the region of the sky you surveyed. Obviously, you didn't survey the entire southern sky, and I'm sure that might have been due to just funding and how much time you had. But I was wondering if you could tell me or tell us about what was the criteria for what parts of the sky specifically. You mentioned overlapping with Sloan at the top, and then Sloan toward the north, and then overlapping with South Pole Telescope toward the south. What about the rest? How did you end up choosing the rest of the sky?
Yeah, well, mostly I think the rest is you just want a continuous piece of sky for a lot of these surveys. I mean, you do worry that you want your survey conditions to be pretty uniform across everything you're studying. I mean, you would worry that, maybe the sky conditions, maybe the conditions within our galaxy, like dust in the Milky Way is different at different parts of the sky you look at. So I think kind of filling in the rest of that area is mostly just we wanted one area of sky that's efficient, that keeps things uniform. And probably if we didn't consider those other surveys, maybe you would have a kind of more normal, continuous looking shape than what you have there, the kind of odd looking shape.
Okay, well, I want to show the Blanco Telescope real quick. I'm showing now the one it just says Blanco _telescope, I think, and this is the 4-meter telescope that Ross has said has been around since the 70s, and the camera, you could see the primary there off to the right. I'm sorry, off to the left a little bit of the.
Yeah, that's the camera's on the right.
It's
elevated.
it's up at the focus in the upper left, right? I mean, upper right. One day I'll get my left and right figured out.
Your other right.
Yeah.
So the camera's off on the right in that picture. Yeah. So it's hanging up in the air when the telescope's observing. So it goes off the mirror, which is at the bottom on the left, and then it reflects back up into the camera, which is sitting up high.
Yeah, so for scale, that mirror is 4 meters in diameter, and this camera is huge. Now, this camera was built by the Department of Energy, or up at Fermilab, right?
That's correct.
Yeah.
Yes.
And so, it's I met a lot of the people that were working on it. It's really an amazing camera. And as you said, it's in the infrared, and it's located
and optical. Yes,
in the
visible and infrared.
Yes, and it's also, and here now I'm showing the Blanco Dome. This is where it's the center dome of these 3 domes here, folks. And
That's right.
This is a beautiful photo, by the way. This is really nice.
It really is.
You can see the large and small Magellanic Clouds up above it, and the Milky Way off to the left. And this is I've been here. This is breathtaking real estate. I mean, I actually could not find a single constellation. Not to mention, okay, so I'm not familiar with the southern hemisphere, but even then, I could still find some things. All I could really see was the large and small Magellanic Cloud, and
it's wonderful to have that problem when you're just blinded. You have no way to recognize the patterns under.
That's exactly right. And I mean, people always say the stars are so bright they can cast shadows, and here this is actually true. On a dark night when the moon isn't out, this is the darkest sky I have ever seen, and they build them here for a reason. And this also is a location, because of the infrared nature of the instruments. The Andes in Chile are a very dry mountain range, very little water vapor, and that's important for the infrared. So that's one reason why they build them down here. And I'm showing now the picture of the dome with the fox. Did you take this picture?
I took this photo. Yeah. I love seeing there's always been 1 or 2 foxes when I've been there observing, and they're more scared of me than I am of them. So it's just fun to see them around.
This is bringing back memories too, because I've seen, I don't even know if it was this exact fox, but this is the walk from the apartments that the astronomers sleep in up to the dome. And and so this is this is amazing. I don't know if I saw that exact fox, but I've seen some. It looks very familiar to me. But this gives you a sense of what it's like up on the mountain. This is Cerro-Tololo, and the name of the observatory, I guess the name of the complex is CTIO, Cerro-Tololo Inter-Agency Observatory, or something
American
like that.
Observatory.
Inter-American Observatory.
That's what it is.
Yeah.
And
this is very much it looks like a desert, and that's because it is a desert, correct?
Yes, it's very dry up here. It's very
Well,
hang on. There's a photo. Hang on. Here we go. Here's a panorama of what you see looking away. If you go to Chile scenery, you can see this is what it looks like looking out over the mountain range, and it's very, very dry. It looks like California to me, if you look out that way. So, okay, well, I want to also show this DECam field of view. I've got that up now, and let me turn that off so we can see it better. So each one of these squares or rectangles in the field of view is one of the detectors. All of them put together is the camera. What's the field of view of this thing?
It's about 10 square degrees, I believe.
10 degrees.
Okay. Wow.
That's huge.
That's a big chunk of the sky you're grabbing. Wow.
Yeah. 10 square degrees. So like 3 by 3.
Yeah. So this is how much it sees at any given time. And what is the size of one image that comes down? An image is a mosaic of all of these chips, right?
Right.
So how big is one image?
What's
the file size? The file size of one raw image.
I'm not sure exactly.
Yeah. So you have to go 500 million pixels times the bit depth of each pixel, which I think, if I recall, was it 12 bits? I can't remember now. but anyway, you multiply that by 12, and there is your, and those are, that's the raw data. But one of the first things they do after they get the raw data is they turn it into floats. So then you have a 500 megapixel image with each one as a double float. So that it ends up being gigabytes huge. Okay, one image. And so let's talk just a little bit about the pipeline, just a little bit, because then I want to get to the science that you're working on.
Sure.
So we've shown the camera. It's 500 megapixels. It's sitting on a 4-meter beautiful telescope, Cassegrain design, that's sitting up on the mountain. You look at 5,000 square degrees of sky over 700 nights to gather this data. What is the process for? Describe for us a night of observing using the DECam.
Sure. So first of all, many DES scientists like myself get to go observing. So we all take shifts down there. So for us as observers, every night starts with a meeting with sort of the operations team for DES to get a plan for the night. And then when it comes time to start, we start the night. So first, earlier on in the afternoon, the technician staff, does the flats, does a lot of calibrations of the telescope before it even gets dark. And then once it's time to open the dome and look out into the sky, the night starts with looking at standard stars, as we call them, just to get to make sure that all the response of the telescope and the response in each of the different color filters is what we expect, or we can tweak. If it's not what we expect, we can account for that for the rest of the night. So we take pictures of stars that are very well known, what their colors and brightness are. And then it's time to start the main survey. So most nights, as I said, we're trying to cover a lot of the sky in these 5 different filters 10 different times. So most of it is a computer algorithm that kind of knows, okay, this is where we still need observations on the sky. And it will know, okay, what is up in the sky right now. We make sure that we're not looking too close to the horizon, because then you look through more atmosphere closer to the horizon. So there's a lot of different factors that this algorithm that we call OBSTAC, or the observer's tactician, it weighs all these factors, and then it decides what's going to observe. And really, for most of the night, the observers there are just kind of checking what OBSTAC wants to do and proving, like, okay, yeah, that makes sense. And we take notes what it's doing. We take notes of the weather. We take notes of which supernova deep field is looking at, because it is important to hit those supernova fields with a high cadence every few days. So that's something the observer tactician keeps in mind. And so a lot of it's automated. And if there are no issues, it's pretty much just letting that algorithm decide things and the observers take notes, checking the image quality so we can get our first kind of raw image, seconds after they've been taken by the camera. And it's always fun to look at them. And, with this new camera, even these raw images look quite impressive. They'll be turned into something cleaner down the line, but we check them, make sure everything's working as we think it should. And then, we do that all night and keep records of everything, and then end the night and talk with the operations team the next evening about what happens.
Okay. You said that you're trying to get the entire survey, the entire 5,000 square degrees of sky that you've targeted. You said 10 times, right? You want to get that. Yeah. You want to get entire coverage of of that area 10 different times. Why is that?
5 color filters, yeah.
In 5 different filters. That's right. What there's so much science that can be done with a survey like this, and I don't want to even pretend to go into all of it. We're going to focus on just your bit in just a minute, because I'm hoping, guys, that that this hangout series with the Dark Energy Survey we'll have them back, and we'll have other people to tell us more about their aspects of the science. So we won't try and cover everything the Dark Energy Survey is doing. doing, but we will try to cover
Sure.
what Ross is working on here. And so, but I would like to get an idea from you. Why 10 times? Why do we need to go 10 and presumably spread out over 10? The time matters, right? You cover the entire sky and then you wait a while and do it again.
So I think, I think they're mostly spread out. So it's not like we observe one place 10 times and then move on to the next. I mean, you could do that, but we tried to do kind of one, we call them tilings, so 10 tilings. So the way the survey worked was, we tried to fill in one tiling across the survey and then a second tiling. One thing that allows us to do is, do intermediary analyses where we have the full 5,000 square degrees, with maybe 4 or 5 tilings or 2 or 3 tilings, rather than 10 tilings in a part of the area. Why 5,000 square degrees? I don't think it's really a magic number. I mean, I wasn't with the team when this was really being planned out, but there are lots of projections of how much sky, to what depth do you need to get these good measurements of cosmology, but there's also the time and cost factor. So I mean, if we had more time and could go even deeper and could get more area, we could do slightly better measurements. So it's not like it's a magic number, but it's a cost benefit analysis, and this was an amount of the sky that we thought we could do a lot of science with. Getting the 5 filters is important. Certain science, because you want each filter with different colors. You can do a lot of different science with different colors of galaxies. So that's certainly important. But overall, it's really just the deeper you can go, the more galaxies you can get. Same with the wider. And 5,000 degrees is where we settled on when this was being planned.
Okay.
So Ross, I wanted to ask you, thank you for that, by the way. But I wanted to ask you, you mentioned earlier about doing a supernova cadence. Sounds to me like you're hunting for supernovae, but could you explain what that is and how exactly that works?
Sure. So the Dark Energy Survey has many different types of science it's doing, but there are a few main probes that kind of get at the main cosmology questions, like what is dark energy? And certainly type 1a supernovae is one of the biggest things to study to understand dark energy. It's the type of thing that was studied that discovered dark energy 20 years ago, that discovered that the universe was accelerating. I think hopefully there will be some supernova scientists on in future hangouts from DES. So I'll save some of the details for them. But in general, we're trying to collect as many type 1a supernovae, explosions, catch them in the act. So type 1a, a supernova goes off and it's an explosion, and it leaves residual light for a few weeks. And how that light initially brightens and then fades is key to understanding properties of that supernova. And then we can tell how far away it is, and then we can get cosmology from that. We can use them as what are called standard candles to figure out the expansion rate of the universe and how it's changing. So the cadence, it's really important that we both see those supernova, and since they last for a few weeks, but we also need to see it multiple times to get what's called the light curve, where we see how that brightness is changing with time. So if we see every supernova field once every 6 days, unless the weather's bad. And that allows us to hopefully get at least 3 or 4 or 5 images of each supernova in the act. So if we weren't doing a strong cadence, if we only visited the supernova, once a month, we might miss some of them, or some of them we might see just once, and we don't have enough information to really use them well.
So if I understand what you're saying, you mentioned this is a type 1a supernova. Obviously, that implies that there are different types of supernovae, and supernovae are exploding stars, right? Just to further clarify it. So you can tell that it's a this type 1 supernovae is special because this is as you said, it's a standard candle. It's a known brightness.
Right.
And you compare its apparent brightness to its known brightness, and that tells you about the distance, correct?
Yeah, that's basically correct. But you also need the light curve to know exactly what its core brightness is. So it's not exactly that they're all the same, but with the light curve, then you can tell what its intrinsic brightness is, and then you can tell how far away it is, and then we can do cosmology with that.
So it's how the light changes over time that tells you, okay, this is really a type 1a supernovae, and this is its intrinsic brightness. Now we can make a measurement. Okay.
Mm-hmm.
So there's been these sort of a controversy, I guess I'll say, between the people who measure the expansion rate, the acceleration of the expansion rate of the universe using type 1a supernovae, and the people who use the cosmic microwave background. And they were getting slightly different numbers that were, and their error bars did not overlap. So that meant that they were pretty confident about their numbers. And the Dark Energy Survey recently published a paper that narrowed that gap a little bit. Is that work that you've done, or is that someone? I'm trying to get a sense of your research at DES. I think it's with dark matter, if I'm not mistaken, but it might have been related to this type 1a supernovae.
Yeah. So, I mean, all these things are somewhat related to each other. So I don't work with the type 1a supernovae.
Okay.
I think one of your future Hangouts.
That's
right. But so what I work on, it is kind of more related to dark matter, but it is also related to dark energy. So I study how the growth of structure, which is what we call it, but it's really how is the matter in the universe changing with time. So we do that by looking at galaxies, by looking at gravitational lensing, which depends on matter. And yes, so kind of more directly, we're looking at dark matter when we do that, but how that's changing is also related to dark energy. Kind of the simple picture is you can imagine, so the universe is expanding. So you can imagine, there's a bunch of galaxies sitting around in the universe. If the universe wasn't expanding, what would you expect those galaxies to do? You'd expect them actually to come closer to each other because of the force of gravity. In the small scales, that happens. So as we see the universe changing with time, evolving to present day, on small scales, the universe is more clustered than it used to be. But on large scales, the universe is expanding at an accelerating rate. So on larger scales, galaxies are getting further apart because of this accelerated expansion, because of dark energy. So whatever is causing this accelerated expansion, and how much is this expansion accelerating, at what rate, and so on, that also affects how this structure changes. And so those are really the two different ways we try to study dark energy. One is the expansion rate, which is more directly measured by supernovae. And the second one is more what I do, which is studying how the structure is changing with time.
And you did this, I think, by looking at millions of galaxies and the gravitational lensing that happened against the cosmic microwave background, or you describe it. What you looked at millions of galaxies in the far early universe, and did what?
Yeah, so we've done a few different projects. So I think the main one that I think is kind of our crowning achievement of cosmology right now, have an image. Which image was that?
Is it DESTNO?
No. That's transient.
Oh, Dev 1, DES Dev 1 mass.
Yes, year 1, Y1 cosmology.
Oh, there it is. Okay, it's up now.
Okay, great. So I'll just talk about what specifically went into this.
Okay.
So this is kind of the height of our cosmological measurements for year 1. So this does not include supernova. I think we can save supernova for another conversation. Supernova studies kind of different parameters. On this plot, first I'll say what measurements went into this plot. So that DES measurement, that is using, as you said, gravitational lensing of 25 million galaxies. So we look at
25 million. I'm sorry, that just blows me away. Go ahead.
Yeah, well, the full survey should have 300 million galaxies.
I know.
So,
Okay, well, never mind then. 25 million.
right. So what we do is we're measuring, these slight distortions in the shapes of galaxies. That if you see them individually, you couldn't really tell. Am I seeing a distorted galaxy from the effects of gravitational lensing, or am I seeing, just a galaxy that looks, the way it does? You can tell that there is lensing at play when, many of these galaxies are distorted coherently, or, in a way that's similar to each other that indicates there's some foreground mass that is lensing lots of those galaxies. So this is called weak gravitational lensing. It's a very difficult thing to study. You need lots of galaxies to find these measurements. So that was one of the things we studied. The other thing we studied is a little more straightforward. We just called what's called galaxy clustering, which I've been a little more involved with, actually, where we just make a map of all the galaxies in the sky. We see at what redshifts or what distances away they are. And we just, look at them and see how clustered they are. So that's very straightforward. We can see that earlier in the universe, so galaxies that are further away, were less clustered than they are now on small enough scales due to the force of gravity. But the weakness of just counting galaxies is most of the matter in the universe is dark matter. So the galaxies do trace that dark matter, but it's not exactly a one-to-one mapping. You don't know that most of the dark matter is where there are galaxies and vice versa, although they are correlated. So the gravitational lensing is important because lensing is done by all matter, both dark and visible. So both of these measurements are important. And this plot is really using those measurements at different redshifts, so different groups of galaxies by redshift, those two measurements, and also a combined measurement, which is called galaxy-galaxy lensing, where you correlate positions of galaxies and positions of lensing. So now I'll say what is this figure? So there are two parameters on this figure on the x and y axis. So the x-axis is what's called omega m. So this is the overall matter density of the universe. So how much matter is there in the universe? And then the y-axis, it's S8, which is a product of another parameter called sigma 8 and also omega m, which is on the x-axis. Essentially, this is a measurement of how clumpy the universe is, which I mentioned before. This clumpiness we expect to change due to gravity over time, but we also expect it to be affected by and it could also be affected in other ways by dark energy, depending on what dark energy is. It could be that dark energy has something to do with gravity, which would change kind of what it does to the universe. So we're essentially looking at the clumpiness on the y-axis and the overall matter density on the x-axis. And you can see that in blue is the measurement DES got, so one of those contours. As Tony was saying, these contours show kind of based on our measurements, based on our statistics, where we think the values of these parameters are. So if we've done everything correctly, we think that there's a 95% chance that the true values of those two parameters lies inside the larger blue contour. So Planck, which studies the cosmic microwave background, does a similar thing. So their 95% contours are in green. And so you can see, interestingly, these kind of overlap. So as you were mentioning, there's kind of this controversy about the expansion of the universe.
Right.
So this is another
H naught, I think they call it. The
H naught to be specific. Yes.
Yeah.
So that one, I think, that one's probably at the top of the heap of kind of debates in cosmology right now. But this discrepancy on this plot here, this is in some ways related, but just in terms of these parameters here, you can see if they kind of overlap, but kind of don't. Yeah, we're kind of still unsure. People disagree kind kind of how to interpret this. The statistics say what is on the plot. By the criteria DES set out before we did this measurement, the green and the blue agree. So we say we do not have statistical evidence that we are in disagreement with Planck on these two parameters. So we're not talking about H naught. That's a discussion for with supernova. For just in looking at the matter in the universe. But you could see that, if we get more data in DES, which we will, we'll have another cosmology analysis probably this summer, and then a final one probably in a couple years. If that contour stays where it is and shrinks, then we're going to be in tension with Planck. And then, what next? There's either we'll have done something wrong, Planck will have done something wrong, or there's new physics we need. Our current model of the universe is wrong, which would be a pretty exciting result, I think.
So you're showing yes, I agree, and you're showing a lower clumpiness, where a lower clumpiness and lower density versus what Planck saw in both coordinates. So you're skewed a little bit to the lower left of this, and Planck has found a higher clumpiness of the universe as a whole versus density. And first of all, I say that the density is higher of the universe than you guys do by a little bit. And so you're thinking, maybe, I don't know what you're thinking, but is it true that if you get more data, what do you think will happen to that blue area? Do you think it will move to the upper right, or do you think it'll stay where it is? What's your hunch?
I will have to be diplomatic on this and say I'm not going to try and make predictions.
Oh man, you were trash talk Planck.
Well, you're not.
I think the Planck guys on, they'll be trashing Des.
Well,
in all seriousness, I think that is the scientific way. We don't. Exactly. I would say probably most people in the field would prefer to find a new problem. And that kind of keeps things exciting. We don't know. And even as I was saying, so this is our current result. And some people, by the criteria DES set out, these results are not inconsistent. We do not have evidence that we disagree with Planck. But it's not a perfect match. We really do need more data to kind of see where things lie.
Okay.
There's one more thing I wanted to mention about this plot that I think is really cool.
All right.
Even let's put aside the tension for a moment. Let's say they agree, or even if they overlapped, that would still be a tremendous result, because for about a decade or two, our best measurements of these parameters, how clumpy is the universe, how much matter is in the universe, came from Planck, CMB experiments. So they came from the very early universe, the first 400,000 years. And it just so happens, the way things have turned out, we have such good measurements of this cosmic microwave background that we can do these really precise measurements, get this really precise parameters for the matter density. But that's all from the early universe. So it's kind of like the analogy we used. It's like looking at a seed and then extrapolating from that, how tall is the tree going to be? And it just happened that for a decade or more, we had really good measurements of the seed and not very good measurements of the tree it grew up to be over billions of years. DES is measuring the universe as it has been, in the past 5 to 7 billion years. So, which is, the second half of the universe compared to the extremely early time of the universe. And even if these agree, that's also remarkable, because it says, we had this theory of what this seedling universe was going to grow up to be, how tall it was going to be. And then we finally measured the tree and it matched, or it almost matches. And it wasn't until this plot, until DES, that we had a measurement of the full universe, the tree, that rivaled that of the CMB, of the seedling. You can see that the blue and the green ignore where they are for a moment, they're about the same size.
That's
that
true.
was never, that's never been true for these optical galaxy surveys until this plot. So that's a really big achievement, regardless of whether it agrees or doesn't agree with Planck.
So to kind of summarize everything, we're looking at the results of two surveys. One, the dark energy survey is in blue, and that's been done at optical wavelengths. Mm-hmm. And the Planck survey is done in green, which represents, in this case, microwave wavelengths. You're almost in agreement, but not quite. And it's going to require a little bit more analysis to see if those two results can further overlap, or if
more observations. They're still getting more data. This was the first year, so.
Right, that's what I'm saying. More observation. Oh, did I say analysis? I meant to say more observations. Yeah, this is just from the first year's data. So now that leads into another question. The first year data was about 5 years ago.
When it was taken, but the analysis was finished summer 2017.
Right, exactly. So that's why I wanted to talk about like what accounts for the delta between when you took the data versus when you're able to present the analysis. Just the amount of time it takes.
Oh yeah, I mean it is kind of eye-opening until you get in the field how long all this takes. As we were saying, we take all these nights of images. Every image is a huge file. It gets stored at NCSA in Urbana, Illinois. And it's just a massive amount of data. So it takes several months we take each year of observations, and we can see the raw images right away. But then it goes through processing for several months to get rid of, satellite streaks, gamma rays, all these various things cosmic rays, that mess with the images. We stack them in all their filters to create co-ed images. Eventually we combine them with, the other times we've observed each part of the survey, the other tilings. So it's a huge, process to just make the initial catalogs of galaxies and lensing signatures. And that just after the several months is when the scientists really start working at it, doing their analyses, and then that takes another several months or more. And really, this figure was in one paper, but it was built on measurements and calibrations from a couple dozen papers. So it's a really big effort. Those year one observations were taken, I think, 2013. We produced that analysis in 2017. We're expecting to have year 3 results. So results with year 1, year 2, and year 3, probably this summer. And then probably our final analysis of the full 6 years, probably a couple years away from that. So it does take a long time. But there's a lot of data there, and we want to do it right.
Right.
So it does take time.
Right. So this is just not something, as you just said, this is not something you just turn around and take it off a telescope and go to work. Well, you take off a telescope, you go to work, but work's going to take you a long time. So
and a lot of people. Yeah.
I just thought that was really cool. Just the way you described that, just all the sheer amount of effort and labor it takes just to getting the result. Taking the data with the telescope is it's literally just the first step in a long series, isn't it?
Absolutely. It's kind of eye-opening, all the different steps. I mean, we have more than 400 scientists in DES. Probably around half of those spend, a significant portion of their time on DES, or maybe, all of their science time is really spent on DES related activities. There are just, so many different things, from the data processing, the data taking. We've got working groups for like 15 different science groups, 10 to 15, something like that. It's a huge project.
Yeah, it's a big collaboration. Here's a picture of it. This is a picture of some of the people involved from all over the world, and this is how science is being done a lot more these days. around the world, and large LSST is like this, and
Yeah.
lots of they're international collaborations. International institutions come together for a science goal, and they contribute. And so this is just a small sample of the actual number of people involved. So it's a big
Yeah.
collaboration.
Mhm.
Okay,
Definitely.
well, I want to get to a couple questions because I'm running out of time here. But Muppet Rathburn wants to know: is it possible that the universe is expanding from the inertia of the Big Bang?
Yeah, I think that's essentially true. That
Wait a minute, really? Because isn't the universe accelerating as it's expanding? Would that imply
right. So yeah, let's get into this in more detail. So I think you can view the expansion of the universe as essentially the leftover. You can picture as a kind of the leftover kinetic energy, momentum or inertia from the Big Bang. So we discovered the universe was expanding in the 1920s. We did not discover the universe was accelerating until 1998.
That's right. Yeah.
So for 70 years, that's essentially what we thought was happening. We thought, okay, the universe is expanding, and it's pretty much just inertia, is one way you could put it. So, and that fit our laws of physics. What made the discovery of an accelerating expansion so crazy is if your basic physics, if you have an acceleration, you need a force. You need something actively pushing on something. And there was nothing, there still really is nothing in kind of our standard model of physics that can account for that. So dark energy is really one of the big mysteries of physics. There's a huge portion of the energy in the universe that we don't know what it is, but there's something's causing acceleration. There must be something there. It's kind of like, just as, inertia is a good way to put it. If you threw a bowling ball, okay, you can let go of the bowling ball and the bowling ball will keep going because it had inertia. But
it wouldn't accelerate unless.
Yeah, if it starts speeding up down the bowling alley, then you're gonna raise your eyebrows like, what is going on?
Right.
There's like some mysterious hand there.
Yeah.
And that's pretty much what dark energy is. There's some mysterious force out there. But when we just thought the universe was expanding, that's pretty much what we thought was going on, and there wasn't a crisis in terms of that that we saw the universe expanding. But when we saw it was accelerating, it was a whole new ball game. Now something's weird is going on.
Yeah. Well, Hans Milling wants to know, back when we were talking about the camera, let me put it up here. He wants to know if some of the tiles are missing. And so I've got the DECam up close image up right now. There's no tile.
Yeah, so I don't think you can see it there. I think it might be in the field of view, or this might be having trouble pulling it up. But
on the right side of the image, or right side of the detector assembly.
I don't think you need to have symmetry over there, but maybe.
Yeah, so I don't think in the images I showed you can see it, but if you actually look at some more modern images, you do see that a couple of the tiles are missing or are blank, and that they're on the edges. They've always been on the edges.
Yeah.
So a couple tiles I think they failed pretty early on, but they were they were on the edge. They weren't a large area, so we've pressed on, and I think one of them got fixed at some point.
Soldiered on.
Are all of the tiles? Because if we toggle between the two, the picture of the CCDs and then the picture of the field of view.
Yeah.
Obviously, you have a slightly different arrangement, and so I'm wondering, are you just not using all of the CCDs that are present in the photograph of the instrument, or are some of them used for non-imaging purposes?
So I never see the DECam as this in this up close view, but I think it's. Oh yeah, it does look different.
Mm-hmm.
I'm not really sure.
Okay,
I hadn't noticed that. Yeah, I don't have an answer for that. Why?
Oh, no
Okay.
worries.
So Neil Yu is asking, what is it that tells you that dark energy is not? Wait, hold on. Yeah, that's what I want to ask. What is it that tells you that dark energy is not simply the geometry of an expanding sphere? And I think it goes down back to that acceleration, isn't it?
Yeah, I'm not sure I understand the question completely.
Well, yeah,
but,
I think so. If you got an expanding sphere, he goes, what is
Yeah.
it that's telling you that it's not simply the geometry of what happens when you have an expanding sphere? But the thing is, that doesn't. Why is it
yeah, I'm not
expanding
sure
there,
how that
Neil?
creates an acceleration.
Yeah, you got to ask Neil, why is it an expanding sphere? What's causing it to expand, right? I mean, it's not just, you can't just say, well, I've got an expanding sphere, so dark energy is what you get when you have an expanding sphere. You got to ask the question, why is the sphere expanding? And
Yeah,
so,
well, and like we said just a couple questions ago, like we've known the universe has been expanding for a long time, and that hasn't raised any alarm flags for physicists. But it's this acceleration that something we're missing something, whatever we're calling it dark energy, but we really don't know what it is. But
right.
it's that acceleration, not just the expansion, that has really put physicists and astronomers on the case to figure out what's going on.
Okay, back to the image of the fox. Hans Milling wants to know, how high above the sea level is this? Some people have problems in thin air, and there is a fox that can find enough food to live in that area. Some people are feeding it, I think. I think you're probably right, Hans.
Yeah, no, I think the chefs do feed it.
Yeah.
I don't know if they're supposed to, but
yeah, it's
I've
not
certainly
good.
seen
It's
that.
not a good idea, but it's they're so
I
cute.
don't know.
Well intentioned.
They're so cute.
I want to say she asked how high it is. I want to say.
Yeah, I don't remember how. It's pretty high. It's like
I want to say like
6,500 feet or something.
I was gonna say 7,000 feet.
7,000. Okay. Quite a bit
Yeah,
lower
so,
than
7,241 feet. Wikipedia.
Okay. So it's actually quite a bit lower than Mauna Kea, for example.
It is. Yeah, so astronomers can sleep up there or at the dorms. So I've never heard of anyone having kind of altitude issues.
It's not that bad. Yeah, I lived in Colorado for
Mauna Kea.
Yeah, I've lived in Colorado for 30 years, and there's some spots up there that really got me. Some of the 11,000 feet and 14,000 feet peaks. They'll take your breath away. Okay, let's see where'd it go. Oh no. Larry Keese, he wants to know about weak lensing. What is it?
Okay.
What is weak lensing?
Yeah, I think I covered it a little bit, but so when you look at a galaxy, a lot of galaxies are kind of elliptical. So you see them. So gravitational lensing, maybe the question is more, I don't know if he wants more gravitational lensing or weak lensing specifically, but gravitational lensing is this effect where light rays are bent. So you normally expect light rays to go, what we consider straight lines, but when there's masses in the universe, they will follow bent trajectories. So famously, this was discovered about almost 100 years ago during a solar eclipse, when they could see that the positions of stars were different when they were bending around the sun. And this really was a confirmation of general relativity, Einstein's general relativity. So gravitational lensing changes the positions of light rays. How much things are lensed depends on the mass involved and how that mass is distributed. So this lensing is a really important tool for understanding dark matter in the universe, how matter has changed in the universe, which, as I said, helps us understand the expansion and dark energy as well. And so weak gravitational lensing specifically is looking at these very small changes you would see in light rays. So specifically, it can change the shape of galaxies. So you can imagine if a galaxy was, tilted like 12 o'clock to 6 o'clock, and then maybe because of gravitational lensing, it would look, 1 minute to the right. So then it would look like it's at, 12 o'clock plus 1 minute and 6 o'clock plus 1 minute. You can imagine kind of a stretched out elliptical galaxy that kind of has a top and a bottom. So these are essentially 1% effects. And, if you just saw that, you wouldn't be able to tell whether, okay, was this a galaxy that's been lensed to be distorted a tiny bit, or is that just the galaxy, that's how it looks? But when you can see a lot of galaxies that look like they're distorted in a similar way, and they're all near each other, and they all could be, their measurements are consistent with some kind of mass that's in front of them doing lensing, and that's a telltale sign. It's like, okay, they're not all just that way. It's more likely they're all being lensed by something.
Yeah.
So that's essentially the idea behind weak gravitational lensing.
Great. Okay. Thank you. And Hans Milling goes like, what do you expect to observe? One thing is what you can observe, but what do scientists believe or models predict dark matter to be? And I believe that's something that you're working on. So what are your models predicting as far as the distribution of dark matter in the universe?
Yeah. So I'd say, there's a model of the universe that's emerged kind of in the last 2 decades that is called lambda CDM, and lambda is the symbol we use for dark energy, or the cosmological constant. It's just really another name for one model of dark energy. And then the CDM is cold dark matter. So astronomers have known about dark matter, or theorized about, seen some evidence of dark matter since I think maybe the 40s. It's been a long time. And there's a lot of, so what we know about dark matter is it appears to be, kind of cold, which basically means it's not moving a lot. It appears to act just like normal matter, and then exerts gravity. So in this model of, dark matter kind of being that cold and acting like normal matter, laws of gravity are as we think they are in general relativity. You can get a prediction for how the matter distribution should be at every age of the universe. So we do have in this sort of fiducial model how clumpy we think the universe should be now, how clumpy we think it should have been 3 billion years ago, which DES is measuring, how clumpy it should have been 5 billion years ago, and so on. And essentially, like in that plot we showed, that model is being put into that plot with the 2 contours we showed. But so if one possibility is, if different experiments, say measurements of the early universe and measurements of the late universe with DES, if they can't agree within that model, it could be that model is wrong, which I think is a very exciting possibility. But so we do have a model of how dark matter works, how it should affect the universe. And we're testing that model now, as well as other alternative models. But that plot I showed is testing that very basic lambda CDM model.
Okay, I got to get to something before we leave. Everybody's freaking out over in the chat about this. It's about time to talk about time, so they want to talk about time. John Suffolk's question is expansion increasing or is time slowing down?
Wow.
How would we know?
Yeah, what does time slowing down mean?
I guess if you've got expansion rates near the speed of light on space-time, and space-time is together, right? It is not, you can't just say space, you can't just say time, you say space-time.
Yeah.
And it's accelerating as it expands. We know what it's doing to space. It's making more of it. What's it doing to time? And do we ever even ask this question? Because I never really thought about it this way before.
Yeah, I don't have a good answer to that question. I mean, I think time is still one of the least understood things in physics.
Yeah. We know what happens in relativity, don't we? But
we know what happens in relativity. And the effects of general relativity are in all these models we're showing.
Okay.
That is important. So we're,
So you are taking that into account.
Absolutely. I mean, these models of the universe that we still use, really the framework was possible once general relativity was discovered by Einstein. And really, it's still kind of the basis of our models of the universe that go into that contour plot I showed. So we absolutely are taking into account relativity. I'm sure there are people who are coming up with alternate explanations of how, what is causing this accelerated expansion. There's a lot of theoretical physics that could be involved. I'm not the expert on that, but certainly any theories that can explain the data and stand up to all the other tests of relativity and physics we have. Certainly that would certainly be interesting to hear, and people try that. But for me, and most people on DES, we're seeing what the data says with kind of the models that have fit a lot of other data right now. And if they don't fit, and if other people have new theories that fits the data, fits everything else, that would be really exciting.
Well, let's think about this just a quick minute. I know we got to go, but what are do you guys know offhand what the units of H naught is? It's in kilometers per kiloparsec per.
So it's kilometers per. It's usually kilometers per second per megaparsec.
Right. Kilometers per second per megaparsec.
Which is strange, but you can think of it as a velocity per
unit time.
Per
unit velocity per distance away.
It's a velocity per distance. I mean, it makes sense if you see.
It makes sense in a non-accelerating expanding universe. The farther away something is, if you think about just linear expansion, the farther away something is, the faster it's going to appear to move away from us.
Right.
However,
so the time part,
we've been confronted with an unfortunate reality. Well, actually, a really cool reality that, while that is still the case, that expansion is even accelerating on top of that. If you can imagine, there's an extra push, right?
Right. So that H naught does change with redshift. I guess we usually say H naught is the present day, kilometers per second per megaparsec, but you could also measure H as a function of redshift, and that does change.
The Hubble constant changes with time.
Yeah, well, maybe you don't call it the Hubble constant. Well, you sometimes see H of Z. I don't know how people usually phrase it. There is an H naught, which is often assumed to mean the present day expansion. Okay. But you can also measure, and intrinsic in all of these studies, in supernova and so on, you're measuring H of Z, and you can. H of Z is not directly the acceleration, but it's related.
Great. Okay. I know that we are really a little bit past our time here, and I know we have a bunch of other questions in both chat rooms. Let me just maybe this isn't. I'm not going to really phrase this as a question, more of a comment for those asking. Some questions about what about finding interstellar planets or any new solar system science. I know, Ross, that's not in your bailiwick, but one of the things that is true about this particular survey is that different kinds of science, including solar system science, has been done with it, correct?
Yeah. I'll just mention briefly some of the other science we've done other than dark energy, but at the smallest scales, DES has discovered a number of what are called trans-Neptunian objects, which are essentially asteroids or minor planets. They're in the solar system that were not discovered until we had this nice deep survey. And even people have been trying to find Planet 9 if it exists in the dark energy survey. But I think one of kind of the more interesting science things that some people in DS have done is using some of the objects discovered by DES, these trans-Neptunian objects, based on their orbits. It looks like there may be showing more evidence that there could be a Planet 9, since the orbits are kind of strange. If you account for a Planet 9, it make these strange orbits then make sense if you model some large Planet 9, affecting the orbits slightly. So I think that's pretty cool. We made this camera and survey to study, billions of light years into the past, and we're also making discoveries in the solar system. And even on larger scales, we've made some really cool discoveries in the Milky Way. One of the first discoveries DS made was finding a whole bunch of dwarf satellite galaxies. So, things like the Large and Small Magellanic Cloud, these little galaxies that orbit the Milky Way. In a similar class, that first plot we showed of the sky footprint was actually also showing what are called stellar streams, which are these little groups of stars that maybe have been disrupted by collisions of the Milky Way in the past, or things coming in. So a lot of Milky Way science has been done. Some of that Milky Way science can be used to understand dark matter as well. And that all of that was not what DES was intended to do. So it's really cool that we've had some of our biggest discoveries, not be dark energy, which is also great.
I know that's what's great about this. There's so much that can be done with wide field surveys taking over a long period of time. Unfortunately, I've got to cut this off. I've got to go, but I want to thank you so much. My guest today was Ross. I can't read my writing now. Cowan. Sorry, I'm getting flustered because I got to go.
Yeah,
Thank you so much. From the University of Wisconsin and Madison. He's a member of the Dark Energy Survey. Thank you so much, Ross, for taking time out to join us.
Ross.
And I hope
you.
we'll get you. We are going to do this again, folks. We're going to have other members of the collaboration back, and we'll talk about other science that they're doing. So thank you for taking time out. On behalf of my co-host, Christian Reddy, I want to thank you all so much for watching. And as always, keep looking up.
Hi, everyone.